I'd like to share with you today how an accurate and repeatable scanner is designed. And this will give you some pointers to look for when you are shopping for a scanner. The key to measuring with infrared technology is using a very accurate infrared sensor. They come in a little transistor case. They look like that. And the sensor has a window. Inside the sensor is a very sensitive set of thermocouples that will be warmed by any incoming infrared heat. And they're very, very, very sensitive. If you don't have some way of focusing your target on that sensor, it's basically looking at an ever widening area for its temperature measurement. So without a lens, without any focusing, if we had a warm dot here, or let's say we were scanning a person and we were scanning their spine, and as you know, the dermatomes go this way, and if we're scanning and want to create an accurate record, we want to be able to have our, if you will, pixel size be small enough to detect changes in temperature from dermatome to dermatome, and very, very precisely. Otherwise, we can miss very small temperature changes that are critical to determining if a person is in pattern or repeating a temperature profile and not adapting to their environment. So we want to measure this small size dot, about 0.3 inches in diameter, which is about the size of the thermocouples on BJ's original scanner. But our sensor, our infrared sensor, without any help, is looking at a very large area and would miss the temperature change, a small temperature change on that spot. So what we start to do in our design is, one, we want to limit the view. And what that takes in the real world is a barrel whose bore is about the same size as the thermocouple head on the original NCM. BJ did a lot of research and came up with that diameter very accurately. So we put a 2-inch deep barrel in front of that sensor to limit, just like blinders on a horse, so that it doesn't look all over the place but focuses forward, that limits only parallel infrared rays to enter and finally get close and reach the sensor. To further enhance, we want a lens here that takes those parallel rays and brings them down to focus on a very small spot within that sensor. The difference in temperature between the scanner and the sensor in the barrels and the target this is the target, the temperature of the man. The difference in temperature between what it's looking at and its own temperature is what the infrared sensor gives us. So it's the temperature difference between itself and the target. Pretty simple. If the temperature of the scanner head, for instance, in your office is, let's say, it's 70 degrees, and the temperature output from the sensor is 20 degrees, we know that the target that we're looking at is 90 degrees. If we know the temperature of the scanner head, and we have the output from the infrared sensor, and we add them together, 20 and 70, we have 90 degrees. This is why when you are using the scanner, we have a thermal barrier or a gasket between the head of the scanner, which houses the infrared sensors, and the handle. As you can appreciate, as you hold the scanner, you will warm up the handle. The gasket or thermal barrier allows the head to only warm up very, very, very slowly. Any slow changes in temperature of the head are compensated for within the circuitry, and we remain reading very accurately. This is why we ask you to always hold the scanner by the handle. When you place it in the base holding the handle. If you were to hold your hand on one side of the head for even 3 or 4 seconds, you would find that the middle graph on your graphing screen would be shifted off to one side, and it would take about 3 or 4 minutes to come back to center. That's why we don't like the scanner when it is not being used sitting next to a warm computer or near a window where sunshine is coming in and warming up one side more than the other. We want the head of the scanner to be of a uniform temperature. Now, measuring the temperature accurately is only one portion of being able to do graphs that are repeatable enough to overlay. One of the things that I wanted to share, again, in the design of a scanner and why our scanner only has 2 barrels. In order to maintain that balance on the head of the scanner, the circuitry that is within the scanner must be laid out, the circuit board itself must be laid out equally, placing amplifiers on both sides equal distant from the center, so any small amount of heat that the electronics generates is generated equally on within the head on both sides. You can't have 3 or 5 or any number other than 2 barrels on a device and expect it to be stable and remain stable. The other secret to being able to overlay your graphs very well for being able to do accurate, repeatable work is the ability to measure distance. The early Titron scanners used a wheel with alternating black and white lines in a circle, and as the wheel turns, light, you can see there's a small red light bouncing off inside of that wheel. Light bounces off these alternating white and black lines, and as the wheel turns, a photodetector responds and gives us pulses every 1/72nd of an inch as the wheel turns. And we calibrate that out so it reads in centimeters on your computer screen as you scan a patient. On the new C5000 and C6000 scanners, that wheel with the alternating black and white lines is actually inside a hub, so you won't see these lines, but they're there. When you pull the trigger on the scanner, nothing happens as far as data recording until you start to move. As you move, whether slow or fast, data is taken every incremental step as that wheel turns. In the middle of a scan, if you just stop, keep your trigger pulled, and hold, no data is taken. So you can talk to the patient, move a bra strap out of the way, and continue on. So just wanted to share that on what it takes to make an accurate instrument.